started. I said the same thing now 3 or 4 times.
Oh,
I'm not going to say it again. I will say it again. So remember moving on now. We were doing the wave equation in d dimensions, and we found that the solution could be expressed, for the general d-dimensional case in terms of the Fourier inversion formula. But what we're going to say is that for specific dimensions, actually we have a very clean expression, involving averages, right? Involving averages of the initial data. Okay. Right, and that the expression is going to depend on the parity, right? Whether the dimension is odd or even dimensional. Okay. So right. So let's see what we need to review here. Right. We have this thing called the spherical mean, right? So you've got some function of 3, right? We find the spherical mean of that function at the point x. Well, that's going to be the average of the function over the sphere centered at x of radius t, right? You take the function, you integrate it over the sphere radius t, and average it over it, you get the spherical average. Right? And we were in the middle of showing a few lemmas. The important one was this one, that if you take something like the Fourier transform of the measure, d sigma, right, of the normalized surface element, then actually it's this function sine 2 pi absolute value modulus c 2 pi modulus c. Okay. And we're in the midst of proving this. We've shown that it was true for a particular c, namely 0, 0 rho, for some rho greater than or equal to 0. Right? And the only thing left to show was that, in fact, the left-hand side is a radial function. Right? So suffices to show that the left-hand side is radial. Right? The right-hand side is radial. Right? The right-hand side is clearly radial. If we showed it for a single point, for that single point we get this value, and we show that the left-hand side is independent of rotation, then we've got it for all c. Is that clear? Okay. So so the only thing we need to do is show this thing is radial, and we'll recall a particular fact. Recall or introduce just a fact that if f is a moderate decrease, then if we integrate over any sphere, we take the integral over some sphere. Well, if we rotate the argument of the function, then nothing happens to that integral. Okay, so this is a fact. The proof of it is, I think, pretty straightforward. It's on the last page of the book, so it's in the appendix. Okay, but it's sort of intuitively obvious, right? You're integrating over a sphere, and then you just rotate the function. You rotate the function on the sphere. Well, you integrate that function, you get the same thing, right? That's okay. So so that basically gives us the radial quality of the left-hand side, because, and so then, if we look at the left-hand side, right, and we rotate it, and we rotate we rotate C, right, we want to show that this left-hand side, we rotate the C, then nothing happens, right? But if we rotate the C, then that amounts to, doing the inverse rotation on gamma. Right? Because that's the property of rotations, right? The defining property of rotations. Right? And so now what we've done is we've taken our function, right? We think of this as a function of gamma. Right? We think of this as a function. We think of this as a function of gamma, right? Then we're basically looking at f of inverse gamma, right? And then we apply the fact. The fact says that, well, that we can just get rid of the rotation then. Okay. So we're going to just the integral of f. So the left-hand side is radial as designed.
Okay.
Yeah, sure.
So we think of the exponent as a function of gamma.
Well, we're thinking of it in sort of two ways, right? First, we think of this whole thing as a function of let's call this f of c, right? This is a function of c defined by integrating this thing, right? Okay. And so what we need to show it's radial is to show that r, if you put in some rotation, then it will change. Okay. Right. So we put in the r, and we move it over to here.
Right.
Okay. Now we think of this thing. Now we're going to think of this as the integral of a function of gamma. Right?
Yeah.
F gamma is sigma gamma, where F gamma is e to the 2 pi c dot gamma. Okay. So, right. So now what we have here, this thing here we can write as pi integral of f of inverse gamma. Right, but we know that that's gamma. Right. Yeah, so don't get confused between the function and the integrand. Right? The integrand is this function of gamma. Right? The function that we're trying to show radial is the integral, which you've integrated out to gamma. Right? The gamma is your dummy variable. Okay. Okay. So that shows that the Fourier transform of this measure has this form. Okay. Any other questions?
Yeah, absolutely. But when we define MT,
Yeah.
why do we not divide by 4 pi t squared? We accept square for the square.
I think that is sort of built into the, like if we were integrating, if we did a change of variables, I think if we did the change of variables, and let y be t gamma, right, then we'd be integrating over actually the sphere of radius t, right? And I think then the factor would come out in the surface measurement. I think it would show up there. I believe. Okay. Okay, so one last lemma, and then with that last lemma, we'll be able to get the solution to the wave equation in R3 in a surprisingly straightforward manner. So here's the last lemma, that if you take the Fourier transform of the spherical averaging operator, then you get the Fourier transform of the function times something like the Fourier transform of the measure. So this is sort of like saying that the Fourier transform of the convolution is a product of the Fourier transforms. Okay, right? This thing here, if you think of it as the Fourier transform of this measure, and you think of MT as, it's not exactly right, but MT is M1 of these, right? M1 is exactly F convolved with D sigma. Okay, and so T, when you put the T factor in, it puts this T factor here. Okay, so the Fourier transform, right? So this is basically saying the Fourier transform of this convolution turns into the product of the Fourier transforms, as we would think. So this is, again, a sort of change of variables problem. So let's think of, so just by definition, MT C, by definition is this, right? E to the negative 2 pi I x dot C times MTF of x, right? MTF of x we change the order of integration. We get integral R cubed f x minus gamma t e to the 2 pi I x dot c dx d sigma gamma. Use Huygen's theorem, and we change the order of integration. And okay, and then you do change the variables. Change the variables. Let's say y be x minus gamma t. Right. So we rewrite this as 1 to 5. F of y e to the negative 2 pi I y plus gamma t dot c dy dx. So you see what you're going to get here, right? It's going to be, it's basically going to be the Fourier transform of y, Fourier transform of f multiplied by some factor. Right? So you pull out that factor, right? You pull out the Fourier transform, you have left over 1 to pi s squared, and then you've got this factor, negative 2 pi I gamma t c d sigma gamma. Nothing is happening. Like, I feel like I did the same thing. And I have. Okay. Well, and then again, I'm going to do nothing. I'm going to move t from here to here, right? Because t is a scalar, right? So I can certainly move it from one side to the other. I'm not going to be right there. From here, t goes from here. Right, but what is that? Right, that is 1 over 4 pi, I guess I'm going to rewrite it. 2 pi gamma dot tc, right? Right? But we recognize this. We recognize this, right? I mean, maybe let me change the order. Right? We recognize this. This is this. Right? But evaluated at tc. Right? So we get sine 2 pi, and t is positive, right? So we get 2 pi c. Thanks. Okay. So it's just like we said, the Fourier transform of this convolution turns into the product of the Fourier transforms. That t, throwing that t in just puts an extra t in on top of it. Okay. So it's like the power of calculus 2. Or calculus 3. It's sort of cool in some sense, right? That all these results rely on on getting your hands very dirty with calculus. There is actually some point to taking calculus. That's what this was telling me. Okay. Okay, so now we can get the solution to the wave equation. Right? So here's the theorem, right? D plus R, the solution to the problem of the wave, or the problem for the wave equation is expressible like this, d dt, t and t f x plus t times answer t g. Right? So it's this derivative of t times the spherical average of one part of the initial data plus t times the spherical average of the other initial data. So, like, if you're thinking of this as R3, it doesn't look like R3. But this is how I'm going to draw R3. Right? This is saying that the solution at x comma t, right? So here's x, here's t, right? Here's x2. Saying that the solution u at xt, right? The solution u at this point, what does it depend on? It depends on the average of f, right? So f is data, f is actually the boundary value of u. But just think of it, f and g are data on the plane t equals 0. Right? Are data on the plane t equals 0. So this is saying that the solution, the value of the solution at that point depends on the average, right, on a sphere around x, right, a radius t, right? Okay. So, right, this is what they call the so-called backwards light cone. If you read the text, they call this thing the backwards light cone. And another way of saying that is that data at a particular point affects things in spheres going upwards, right? In spheres going upwards, right? So this is the propagation of the effect of the data, right? What is this effect? It affects the solutions at these points, right? Right? Because at each point, if you draw a backwards like cone, that includes that. Right? At each point up here on the cone, if you draw a backwards like cone, it'll include this point. Right? So the data at this point affects everything, affects exactly those points on the forward like cone. Okay. And this is so-called Huygen's principle. Does that make sense? Because we're gonna use this. We'll use this fact in the method of descent to get to the solutions for the even cases, even dimensional cases. Okay. So this what we see here is that the solution is determined by the data on this cone back here. Right. Conversely, that the data at a point affects only the solutions on the forward leg. Okay, so this is pretty cool. And let's see how we do it. So we break the problem. We consider two sub-problems. Some sort of sub-Cauchy problem, or Cauchy sub-problem. So first, in case of when G is equal to 0. Okay, so F can be any Schwartz-Class function. G, however, is required to be 0. And the next we'll do the opposite. We'll say F is 0, and G can be anything. Okay. Using the inversion formula expansion, the inversion formula expression from before, we see that the solution, I'm going to call it U1 in case 1. We see that the solution, well, it's going to look like this, because the G is 0. Cosine 2 pi mod and absolute value C T E to x B C. Okay, right. This was the Fourier inversion expression. Originally there's this other term, but that other term depends on G. G is 0. And then we do something sort of humorous. We write it like this. Humorous and really clever. We express it like this. Sine cosine C over 2 pi cosine C. This is cute, right? Oh, it should be C. Right? So we put in this T here, right? But we don't put in a T. And we say, well, differentiating with respect to T turns this into the cosine with some factor. We divide that factor. Right? So these two things are the same. So top one. Okay, top one, and then math 139, right? We recognize this. What is this thing, right? You recognize this. We just said this thing is the Fourier transform of the spherical aggregating operator. Right? We're taking the inverse Fourier transform of the Fourier transform, right? And so we get dEt. T times mt at x. second case, we do something very similar. Right? So case 2, that is 0. In that case, right, U2 is going to be, well, we just have the other part, right? G hat C sine 2 pi C CT over 2 pi C in this Fourier transform. Right. Now we do something even less, what? We do something even less mysterious. We multiply and divide by t to get the t in there. Okay. Right? So right. And now we've got T times the spherical average G. Right? Okay. So then you say, okay, well then for the general solution, well, it's a linear, it's a linear problem, so you just add these two solutions together, right? And so the solution to the general Cauchy problem would be the sum of these solutions. So you get, the general solution is going to be U1 plus U2, which is what we want. Okay, pretty cool, right? Isn't it cool? I'm glad I'm teaching this course. I actually never done this. Just to confess to you. Actually. But I can see I can teach it. Yeah, like I said, my field of specialty is the future of Fourier analysis, harmonic analysis. And I unlike some of my classmates, stay basically within Fourier analysis. Although it's very profitable to actually look at the intersection of that and PDs. That's actually really, that's a good place to be. Like I said earlier, I worked with Thurman. There's another mathematician at Chicago called Kenny. Kenny is more like the intersection of Fourier analysis and PDs, or more PD. Those who went to Kenny went to the PD. Okay, so that is the solution. That is the formula solution in R3, and it's apparently due to Hadamard, the mathematician Hadamard. Like the spherical averaging operator is defined by Hadamard, and I think he's responsible for this solution as well. He's also responsible for this idea of the method of descent, which is to go from the solutions in the odd dimensions down to the solutions in the even dimensions by taking your initial even dimensional data and then extending it to one more dimension, right? In a very obvious way, by making it constant along the third dimension, basically. Making it constant along the third dimension, and then you solve the wave equation in the odd dimension and drop it down to a solution in the even dimension. Okay, so you start off with your, I'll say it again. You start off with your data, right? It's on R2, and then you say, okay, I'm going to make it data on R3 by making it just taking copies of it and making it constant up and down. And then I'm going to solve the wave equation on R3, right, using this initial data, right? And then I'm going to basically, just drop it down to a solution of the wave equation on R2. Okay. So, but there's some things that you have to watch out for. First off, the main thing being that when you extend, if you extend it to constant, then you don't have a Schwartz function anymore, right? Because it doesn't vanish. There's no, it's not decreasing, right? There's no decrease. It's constant, right? And so you can't do that. You can't do that. Okay. But it turns out that what we'll do is we'll do it by using bump functions, basically. We'll say, okay, we'll make a little bump function that's one, in this region, and then decays after that. Okay. We'll make and then we'll solve that problem, we'll get a solution. And then what we'll see, using Huygen's principle, is that, no, not using Huygen's principle, but what we'll see is that if we extend the bump function, then what we get is a solution. So we'll make a bump function that is constant between two bounds. Okay, it's one between these two bounds. So that we'll extend these guys and they'll be constant up until these places, and then they'll start decaying. Okay, so that we satisfy Schwartz, the rapid decay. Okay, and that when we do the drop down to the solution, will give us a solution within a certain range. Okay, it'll give us a solution within a certain radius. Okay, t. Okay, and then what we'll see is that if we extend t, well, we'll get another solution for the bigger t, and it will agree with this one. It will agree with this solution. This is the thing. It will agree with this one, and so we can sort of bootstrap our way up, right? We take t to be arbitrary, and we just extend. We get a bunch of guys that keep on agreeing. They agree on the areas of overlap, and you can use them to develop a function at whatever point. Right? So you can figure out the value at any point by just extending it past that point, and that will be the solution. A little bit intricate, and it does involve Huygen's. Okay, so wave equation in R2, we got Hadamard's, method of descent, and dropping from the higher odd dimension down to the lower even dimension. So we're going to need the following definition. Say it's a function on R2, and we define a weighted average. So this is not the same average as before. It's going to be this. 1 over 2pi f x minus ty. 1 over 1 minus absolute value of y squared y integrated over the disk of radius 1. Okay. So instead of taking the average over a ball, right, we're taking some sort of average over a disk, right? Average over a disk, but it's weighted, right? The values are weighted, right? So that you've got this, you've got this thing, you've got this weight on the values of the points. Okay. And so the theorem is you have f and g in the Schwartz class on R2, and these guys are the Cauchy data for the wave equation. Then the solution in this guy is a solution where this guy is this. dt t mt twiddle f x plus t mt twiddle g x. it says that the solutions don't depend on a hollow cone, right? That the value here doesn't depend on just the boundary of the cone down here. It actually depends on the whole solid cone. Okay. And similarly, going forwards, right? That this guy doesn't affect things just on the boundary of the cone, but it affects things on the whole, right, on the whole interior. And so this is, at the end of the text, at the end of the section, they comment that the difference between light and water, right? If you flash a point, have a point source of light that flashes just for a second, well, eventually you'll see just a flash, and then after that, nothing, right? But if you have water, right, and you hit it first, if you make it, if you hit it at one point, then eventually you are going to start going up and down, and you'll keep on going up and down basically to the end of time, right? Except in reality, right? But basically, if there were no friction or something like that, anyway, theoretically you would go up and down forever, right? And so this is the difference between the even dimensions and the odd dimensions. And this is how it shows up. This is how it shows up. Right? The difference between wave behavior in odd and even dimensions. Okay. Because we have a solid like on here, and we just have the edge, just have the boundary. Okay. So okay. So here, let's go. Let eta in SR be basically some sort of bump function such that eta of x is 1 whenever x is less than or equal to 3t. So fix on t. Fix on t, right? We're going to then we create F flat and G flat in the Schwartz class by taking our old guys, right? We take the old function at x1 and x2 and then multiply by eta of x3. Right? So this guy will be constant equal to f of x1, x2 as long as 3 is between negative 3t and positive 3t. Okay? So it's going to be, this thing is constant between a certain range of x3s. And then after that decays because we need these guys to be in the Schwartz class. So you can do the same thing for similarly for G flat. Okay. So now now this is our data for the three-dimensional wave equation. Right? So we have a solution U flat for the Cauchy column in R3. Right? We take this as our initial data, run the stuff that we just completed. We get the solution here. Right? And let me see if I can draw this. So basically by Huygen's principle, for t less than big T, in absolute value, UB xt is constant in x3 for all x3 less than t. Okay, let me see if I can make that clear. So along the same lines as before, let this be R2. Okay. This is my R2. Okay. and then here's my r, right? So I have initially, like here's my x1, x2 guys, and here are my x3 guys. Okay, and I've extended the data so that between 3t and minus 3t, the guy is constant, right? The data is extended constantly in this direction, right? And then starts decaying after 3t, but it's constant between here and here. Okay. Okay. So now think, right? Here is 3t, 2t, 1t, 1t. Right? Okay. Here's t. As long as my t is less than that big T, right? So my height at worst is, and I'm going to take my x3 smaller than t, right? So here's t, right? So at the worst, I'm going to be here, right? At the worst, I'm here. My t is capital T, and the size of my t is capital T, and the size of my x3 is capital T also. This is the worst. This is the boundary. Okay. And you think, okay. Well, we're thinking about U flat, right? Well, U flat, by Huygen's principle, U flat depends on this cone down here, right? The cone of radius t, right? Okay, but that cone of radius t lives within the negative 3t world, right? Right? And what I'm saying is that it's constant in x3 as long as x3 is less than t. Right? So it is minus t. And I'm saying that if we move along this way, it's going to be the same. Right? But that's obvious, right? Because our initial data is constant between negative 3 and 3t. So, along the third variable. So if I slide the cone around in the third variable, and the cone never leaves the 3t world, then it's constant. Right? We're taking averages of things which are constant in the third variable. Okay. This is the picture. Anyway, so we slide this thing around here. We're just staying within the place where the initial data is. Where, like in here, right? F flat and G flat are constant in x3. Right? And so you're taking averages of guys who are constant in x3, and so the solution is going to be constant in x3. Okay. Okay. So now. Okay, so now we create the solution. Define u of x1, x2, t as u flat of x1, x2, 0, t. Okay, so right, we just take the values along this line here. Okay, right. We make a two-dimensional solution by just looking along that two-dimensional thing, right? And you see that U solves the two-dimensional Cauchy problem for t less than t. Right? Okay, so now we come to the point which I mentioned before. You might be, at this point you let t increase, right? You can take your t to be, t is arbitrary, so we can do this for any t. Right? Can do this for any t, right? And the only thing you might worry is that do we get a different solution every time we change the t, right? But if you think about it, right, if you increase the t, right, if we increase the t, here's t2, and t2, blah, then the new solution is going to agree with the old solution up to t, at least. Right? It'll agree with the old solution up to here. and give us a new solution past that point, right? Because we're taking averages, right? The old solution depended on averages of the function here, right? The new solution up to that point depends on the same data, right? You're just taking averages of the same data, right? So you're not changing the function up till that point, and then after the point you get more, but it agrees with the old function, right? Because you're averaging the same data, right? Okay. So right. Notice that if we take T2 bigger than T1, then UT2 agrees with UT1 for T less than T1. Okay, and so we can, since T is arbitrary, so in this way we obtain a well-defined solution U x1 x2 t for all t. For all t. And so the only thing left to do is to show that this solution is the same thing as the solution that this solution actually does have the form that we wanted. I could do it. I think I probably could do it in 1 minute, but it wouldn't make sense. Okay, so sorry.
We have an exam.
Okay, if you give me 1 minute, please. Thank you. Okay, so here's basically what's going to happen. We have 1 minute. x1, x2, t, by definition, is u flat x1, x2, 0, t, right? Well, we know what this is. We know what this is. We worked this out already. This is ddt of t, mt, f flat x1, x2, 0, plus t, mt, g flat x1, x2, x2, 0, right? This is the averages of the extended initial data, right? So the only thing we need to do is to show that if you take a function that is constant in the third variable, then this turns into t mt at f, and this turns into t mt at g, right? And if we can do that, then we'll be done, right? Because this is what we want to show. Okay. And I'm not even going to show this, because this is a trivial calculation. This is a calculus 2 calculation, even though I've shown all these other calculus 2 calculations. It's easy to see, and if you want, I have it in the notes, just to see that if you take the average of a function that is constant in the third variable, then you get this this weighted spherical average, weighted ball average. So that's it. Okay. Exam next time.